Any hard shell kayakers here? Oh, I think I asked that question before. I also used to do that, not at this proficiency, also in medieval times. So, yeah, fine. Quite amazing, really, isn't it? Surfing West Virginia, as they call it, or Pennsylvania, on the Lehigh. No, this isn't. I'm sure. I'm sure this is the New River or the Gauley in West Virginia. But the Lehigh is a well-known kayaking river for those of you in the west. The Yuck, of course, south of Pittsburgh. Nice dam-controlled river that keeps the outfitters running water through it all through the summer to be able to make a livelihood out of it. Big livelihood. And where it is in the mountains. So yeah, cool. Who did something exciting over the break?
I guess the closest thing to would probably be visiting family over in central PA, if you've heard of it.
Schmoke, is that you call that Central PA? Isn't that Scrantonish?
It's much further. It's a bit further out.
Further west?
Yeah. It was nice.
Yeah.
Just I was driving back and it was actually pretty ugly out. Not weather-wise, but more so because everyone was driving like a lunatic, and there was construction along the majority of the roads. So
Is this Highway 6?
I think
Runs the northern tier.
I-80 to I-33.
I-80, fine. I-80, yeah, fine. Yeah. Well, it's never a time to be traveling over Thanksgiving. Not the best time of year to be traveling or being caught in an airport. Who went to Florida? Nobody? There's one of you who's going to Florida to stay with her 40-year-old boyfriend. I think it wasn't the case. She said he had a condo, but I think she meant his parents had a condo. So, yeah, good. So, welcome back. I guess we're getting towards the witching hour. Thanks for participating in the midterms. I think they seem to work out well. It's always a very personal thing as to whether they do or not. Certainly for everyone, the second one worked out quite well. I don't know what happened to that. And so I appreciate your email early on saying, should we do it in the evening? But I'd already decided that since the university was so candy-ass in cutting classes for essentially a snow date that didn't come a snow date, I was sitting with a cappuccino and a brandy at London Heathrow at 10 o'clock in your time, 10 o'clock my time, 5 o'clock your time, and I couldn't see on my weather app that anything was happening in State College, so I was kind of annoyed by that. Probably great news for you that I was annoyed because I just said, yeah, blow it. Not going to reschedule it. So we didn't reschedule it. But, so anyway. So we're almost done with tests. Tests will be next week. The finals, they're worth less than 10%, so they're worth slightly less to sit with faculty senate or Penn State Senate regulations that, it is the New River, that anything in final, the week before last week of classes should be worth less than 10%. So that's the deal. The review stuff is online, so you can see that if you haven't looked at it already. And it is, and the materials are defined exactly what they are. They'll include the stuff that we talk about today for this week. Set this off. So the last part of pipe networks, there's a network question, there's an external flow question, and there's an open channel flow question. And so the material for that is on there. So it's kind of standard. Again, they follow previous tests. They are verbatim. So you can choose your review to be able to accommodate that. So same verbatim, near verbatim tests, maybe with numbers changed, maybe not. So So that's the final deliverable. So good news is that you're reaching the end of the marathon with this final sprint. If you're signed up for a conflict test, those will be in finals week, in the finals week slot. I haven't looked to see what that slot is yet, but I think it's on the Tuesday. And some of the people taking the conflict exam have conflict of the conflict test, so that's on a slightly later date. So it's either on the Monday and Tuesday of exam week if you're doing that. You've got your presentations in. I think we only needed one per group, so people have been worried about whether they needed to submit ones themselves. I'm sure that's not the case. The peer review thing came out last night, so you can comment on your colleagues and how much effort they put in. That gets rolled into the 15% of the grade for the presentations. And I think there'll be one homework for this week 13, which I guess is probably due on the Friday of the last day of class, on the last day of classes, or that weekend, I'm not sure. I can't remember. But anyway, so there's one more homework left. So that's done. So that's where we are. So congratulations. We're getting to the end of the journey on this. Been fun having you in the class. So, questions? It's pretty straightforward, right? Great. All right. Well, we were surfing West Virginia, and so our very last topic, and perhaps we can review things from the last little while. But our very last topic is open channel flows. And so the deal with open channel flows is that unlike pipe flows, which completely fill the section of the pipe and are constrained to that volume, and external flows, which completely envelope the structure that they surround, open channel flows have one free parameter, and that is the depth of the channel. And so that is the reason why you get, when we look at surfing West Virginia, this weird and wonderful behavior with these waves in the channel at very high flow rates. And so if you don't constrain the flow to completely fill the, this is it, I guess, to completely fill the cross section, then you could imagine that it could flow to be a very shallow flow, flowing very quickly, or to be a very deep flow downstream, flowing very slowly. And actually, why don't we look at that? This is the previous example here. This is exactly what this is. And so a hydraulic jump is when it jumps from being exactly that. So on the left-hand side, if you cut this anywhere along its length, the flow rate across that section has to be the same from continuity requirements. Q upstream has to equal Q downstream because it's not accumulating anywhere. So if you cut it upstream, then it's a very shallow flow depth, a very small cross-sectional area. So the velocity times area there has to equal the velocity times area on the downstream. And so on the left, by definition, it has to be flowing quickly, and on the right, it has to be flowing, I also have to check to see it's the same orientation. It's flowing very slowly and at a deeper depth. And so that's the issue for open channel flows, in that you can have each of those modalities that the water, if you like, gets to choose between. It can choose between whether it's going quickly at shallow depth or or more slowly at a deeper depth. And so that's some of the things that we'll talk about in this class, in this last week or so, last 3 classes. So what we will talk about, so that is, so in terms of the things that we'll talk about, is this working? I'm going to recap what you did in week 12 and 10 and 11 first, but we'll talk about these flow classifications. And it turns out that we can flow as uniform flows, where the upstream and downstream depth are the same, or as gradually varying flows, where the depths change as you go down, and as rapidly varying flows, where it is like in this hydraulic jump. And we can talk about these different components. But let's, before we do that, just catch our breaths and look at what is the same in what we've done so far. For pipe flow. I'm going to draw something on the left-hand side which is tall, which you'll see, and I'll pre-draw it perhaps. I'm going to draw something like this. Our Moody charts, essentially. I'm going to draw 3 of them. One for pipe flows, one for external flows, and then one for open channel flows. Just to identify everything in the same space. So this is the boundary between turbulent and laminar. How's my writing? This is friction factor. This is drag coefficient or lift coefficient. And this is Manning number. Which we haven't talked about. This is Reynolds number in each case. We know that Reynolds number is equal to a velocity, a density, a characteristic dimension, hydraulic diameter, and a viscosity. It's the same for each of these. And we know that, for instance, HL equals delta P over gamma equals friction factor times length over diameter times V squared over 2G. V is the average velocity. This is a Reynolds number of, say, 2,000 or 1,000. And we know that here, this is friction factor, I'll probably just draw it small, is equal to a constant divided by Reynolds number. And these are for increasing values of relative roughness. And so we know that in the laminar regime, friction factor is a function of Reynolds number but not roughness. And we know that in the turbulent regime, it's a function generally of roughness but not of Reynolds number because these lines are horizontal. You know that maybe for open channel flows, that what if they looked like, some of them have looked like this with a little divot and then this. And then this has also been a constant over a Reynolds number. And this has just been a single value, say, for a sphere. And we know that physically what these represent are different flow regimes. They look the best when we do them for flow around objects because this is the one where it hugs the object. And this is where you have this von Karman vortex street coming off the back, which is the reason why the Tacoma Narrows bridge got pinged like a guitar string as these individual vortices are shed periodically from the top of the box girder and the bottom. And if it happens to be the resonant frequency of the bridge, then it pulls it apart. And what do we have? If we go back to this, we have coefficient of drag is equal to either drag force, squarely D. So this would be a lift, or this would be, I guess it would be the other direction, wouldn't it? This would be drag. This is squarely D as well, is equal to a half density velocity squared. The velocity is the far field velocity, the relative velocity between the object and the main stream, and the area. And of course in this, oh, that's quite good, this is equal to delta P, right? A force divided by an area is delta P. And so we could also write this as delta P equals CD times a half rho V squared, just multiplying this bottom. If we divide it through by delta rho G, which is unit weight, this term here, this would be rho G, then HL would be equal to CD times, these cancel out, V CD times 1 times V squared over 2G. I put the 1 in here just because we have this modifier here, so this is equivalent to the friction factor. This is the velocity, the far field velocity of flow, not -2, but average velocity. And this is the head loss that is happening. We don't really think of it as a head loss. Here we're thinking of the head loss in a pipe that occurs between upstream and downstream. That's our interest. In this, we're interested in the force that's applied rather than the head loss, and so, but it's equivalent to that behavior. And in this, as we'll see, we could imagine that for an open channel flow, see how my drawing is? No, it's not too bad. Get the picture. Get perspective. It should narrow as you go down to the vanishing point. And so this would be either a velocity or a volumetric flow rate. Doesn't really matter. And actually, we would think that we would have curves like this. Again. So we could just do some experiments in different flumes to be able to look at what the behavior is. And we'd find out that this, what was this? This was maybe, was this 10 to the -2 and 10 to the -1? I think this was 10 to the 0, and this was 10 to the -1, just in terms of ranges of these parameters. And I think this is also 10 to the -2, 10 to the -1. This so-called Manning coefficient. And these would be for increasing channel roughness. Kind of a surrogate for epsilon over hydraulic diameter. So this is relative roughness as it gets rougher and rougher. So these are pipes that look like this. These are pipes that look like this. This is the locus of all the smooth components. And this is for a glass flume, and this is for a weedy flume for these. And so what this does is it really identifies external flows. If I put labels, and open channel flows. And open channel flows. So that puts them in the same frame. If we were always guaranteed to have pipe flows which were in the turbulent regime, then we'd only need these components. It turns out that for open channel flows, because the Reynolds numbers are always large, almost always will they be turbulent, and almost always we can classify them in terms of a single number for weedy, glass-filled, concrete-lined, etc. There'd be a single number that we can use. And so in some respects they're always on the right-hand side of this line. That's not the case for either external flows or pipe flows. We can't make that supposition. But almost always it turns out that for open channel flows, we're on the right side of this line, turbulent. And so we can deal with it as this. That puts it, everything we'll talk about for this part of the class, and actually since class of 10, week 10, 11, 12 was external flows, and 13 is this. So for 4 weeks, it really conforms to this behavior. You've seen this before. I'm not going to leave it up super long, so you can write it down. The same thing. Yeah, you've seen this. This is the same kind of summary, a bit messy, but if you look at pipe flows, external flows, and open channel flows, the differences are just, well, you can evaluate them in terms of dimensional analysis, and you can look at how many parameters describe the flows, and you can come up with the relationships that describe these behaviors. And the bottom line is the bottom line here, is that these Moody charts and the coefficient of drag or coefficient of lift charts and the Manning charts all conform to the same thing. The only thing about the Manning charts is that we're working on the right-hand side of turbulent, sort of turbulent flow. So that's a figure that kind of explains what we just drew out and you just have. So that's what we will do today. So what makes open channel flows open channel flows? I'll use the notes just because I have them. So of course you can have an open channel flow in a pipe. The main component is that rather than driving it by an upstream pressure and a downstream pressure, it has to be driven only by gravity. So all its driving flow is the self-weight of the fluid that wants to get from high potential upstream to lower potential downstream. Even if you fill the cross-section of this pipe, and if you had, say, the water level at this level here, and the outlet water level at this with a tiny little air gap, that would really be gravity flow. The idea is that you can't really sustain an upstream pressure and a downstream pressure because it'll short circuit in the air above it with very low viscosity. So it's only being driven by the elevation of the surface of the water, which might mimic the elevation of the pipe, or it might not. So you could imagine that this free surface of the water would have exactly the same slope as the base of the pipe, or it might not. And so those are the different flows that we'll talk about. So driven only by gravity. We know that to maintain the same regime, as we talked about here, this regime versus this regime, we index it versus Reynolds number. And we've said that we can do that here. It turns out that there's also another number that is important for us, the so-called Froude number. Can never work out how to pronounce it, Froude or Froude, don't know. But just like Reynolds number is the ratio of inertial forces to viscous forces, the Froude number is inertial forces to gravity. And so you've seen it before. It's if you set the Froude number equal to 1, and this is the velocity of a wave, the velocity celerity wave is equal to g z. You've seen this before. So in other words, if this Froude number is equal to 1, and this is the depth of the water. So if this is the water, this is the wave that's traveling in that water. And this is just kind of interesting relationship. This is just how deep the water is. 10 feet deep in a swimming pool, 1 kilometer deep in the ocean. This is the speed that the tsunami wave goes at, which we probably did in the first class online. Peng Liang took the first ones, right? So this is the ratio of inertial forces to gravity. Okay, and it's an important number for us. It's only important when we're talking about gradually or rapidly varying flows, because it's the rate at which you can signal upstream. If you have a hydraulic jump, So you have water going at some fast speed and then it's jumping into this plume downstream and going more slowly. The only way that information can go upstream from that point to any point upstream is by going upstream by a signal of the velocity of the celerity wave. So if the water flow is faster than this wave speed, you can never communicate upstream. I suppose it's like shouting into the wind. If the wind coming into your face is going at the speed of sound, 600 miles an hour, no one will ever hear you upstream because it will never go against it. If it's going at 0, they'll hear you. If it's going at half the speed of sound, they'll hear you delayed by a lot. If it's going at the speed of sound, it will never get away from you. And so that's the rub there. The other thing about open channel flows is that the Reynolds numbers happen to be large, and so we're almost always turbulent. So we've used before the hydraulic radius, hydraulic diameter, which is 4 times the wetted area divided by the perimeter. In open channel flows, by definition, we'll use the hydraulic radius, which is the area of the perimeter. I've never quite understood this. If you use the hydraulic diameter and you use 4 times pi d squared, and you divide by pi d, pi d squared over 4, isn't it? Over 4. Then you get rid of this, 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 and you're left with the hydraulic diameter for a circular section. So this would be for this, right? Whoops, that's not circular. Where this is the area and this is the perimeter, is just d. For this, you don't get this. The area, if you imagine it filling up a circle, then the area would be pi d squared upon 4. And the perimeter would be 2 pi r, pi d, which is equal to, once you do all the substitutions, d over 4. And so hence, for some reason, the hydraulic radius is defined as 4 times the hydraulic diameter, rather than 2 in a regular case. And so the corollary with that for pipe flow and channel flows is that if you do the calculations for the transitional Reynolds numbers, where we go from laminar to turbulent, maybe at 2000, then if you classify it in terms of hydraulic radius, then and use hydraulic radius in your Reynolds number on the bottom axis of our charts here. So Reynolds number could be equal, it could be, it's our choice what we choose. It could be velocity times density times dH. Or it could be velocity times density over RH. It's up to us to choose. And obviously all our classifications would be based on that. And so if this is defined in terms of hydraulic diameter, then this indeed would be 2000. But if it's defined in terms of hydraulic radius, then it's actually 500, because of the relationship between hydraulic radius and hydraulic diameter. So that's all this little chart is pointing out. And it turns out that if you look at any numbers to represent a channel, because channels are quite big, then it turns out that you're always above that number. So if just imagine a ditch, which is 10, or a stream, which is 10 feet wide, 1 foot deep. Hydraulic radius is area is 10 feet by 1. Perimeter is 1 foot by 10 foot by 1 foot to give us this. So this is the hydraulic radius, which is almost 1. And multiply that by a Reynolds number if we're going at 2 feet a second, the density of water, the viscosity of water, apologies in English units. But Reynolds number obviously is in terms of dimensionless. And so this was hydraulic radius in this particular case. So we'd want this to be 500, greater than 500. And 1.4 times 10 to the 5 is, of course, much greater than 5 times 10 to the 2. So almost all cases we can imagine this is going to be turbulent. So then the classifications come to bear as to what we expect from this. If you imagine flow from some kind of pond downstream across a weir, we use weirs, as you might remember, to measure the height of the water above the weir, and we can convert that into a flow rate. The higher the water depth above a weir, the higher the flow rate, and we can classify that according to Bernoulli's equation and some other variants on that. But we can define different series of flows, and you see these different flows are referred to as the simplest one, which are uniform flows. And so what uniform flows are when the upstream depth is equal to the downstream depth of that segment. In other words, what's uniform is that the depth of the flow is uniform. If we think of this as being a depth y, and we can think of it either as being a depth y, or we can think of it being as a depth perpendicular to that. It doesn't much matter because these angles are so small. This slope of this bed is quite small compared to the horizontal. So it doesn't really matter whether we define it as a vertical height or as a normal to the bed dimension height. They're pretty much the same. Uniform flows would be where it doesn't vary much between upstream and downstream. Gradually varying flows are where it's a bit deeper upstream or downstream than it is away from it. And rapidly varying flows would be when there's a big difference, right? For this one, it starts off here, ends up here, and it behaves differently. And so in each of these classifications, we have to seek a different kind of phenomenology for the flow. And so that's what we'll do. So what we'll do today is we'll talk about only the simplest of those, which are uniform flows. And I guess the other classification is we'll talk only about steady flows. So we won't talk about flows where it's varying in time. And so we looked at the Malpasset Dam. When you get the breakage of the dam and it all flows downstream, that's not steady state because you start off no flow downstream and you end up with some flow downstream that must ultimately stop. And so some of these cases are not steady state, but that's not really our point here. But for today, what we'll deal with are these uniform flows. And so that means that as you go from upstream to downstream, you have a bed which varies with some slope. And so this would be L. So S0 is equal to delta, I'm not sure what we can call it, perhaps call it H. Delta Z. Let's call it delta Z. Delta Z over L. So it's just the gradient. It's like the gradient on a road, 1%, 2%, 10%. And so this is the slope of the bed. We know that we can draw in Bernoulli, right? We could do this as, this would be Z upstream, this would be Z downstream. If these Y's were actually vertical rather than angled normal to the bed, then this would be the pressure head acting at this point, right? So this would be, this point here would be the total head. So H would be equal to YU plus ZU, I guess, right? This would be what we've referred to as head. And in other ways, this would be equal to pressure over unit weight, be the pressure at this point, no different than that. And if the depth of flow upstream and downstream are the same, then these have to be the same. This free surface would there be defined by a slope of the free surface, which would be the same as the slope. This is the slope of the bed here. If YD and YU are the same, then the slope of the free surface, the slope of the water, if you like, has to be the same as the slope of the bed. And therefore, if the flow rate across here, since Q upstream has to equal Q downstream. The areas of flow are the same, so the velocities upstream and downstream have to be the same. So V squared over 2G upstream and V squared over 2G downstream have to be the same as well. So the bottom line is that if we require that the upstream and downstream depths are the same, i.e. uniform flows, then by definition, the slope of the bed and the slope of the water surface and the slope of the energy grade line all have to be the same. So simplest case. If upstream and downstream flow depths are not the same, then they can all be different from each other. And those are non-uniform flows, which would be either gradually varying flows or rapidly varying flows, which you have to deal with. Okay? So the case that we'll deal with today is this. If you take a section along the length of it and draw a cross section, A prime, or AA in this case, this would look like this. If it's a segment, it can't go infinitely wide in this dimension here. It's got to have boundaries to it. And so it would look like this. If we look at that section, then we have wetted perimeter, which is we've called P. And I guess we have an area of flow, which we've called A. And those are the things we need to worry about. Let's not worry about that for now. We can come to that later. If we look at the section and we look at the velocities and contour the velocity, you could imagine that if you drop a stick into the stream and you drop it close to the bank, it will travel less quickly than it would do if in the middle of the stream. And also, that is because on the edges you have this viscous drag. Actually, it's not viscous drag, I guess, but it's like viscous drag because it's turbulent. We've said it's always going to be turbulent, this interaction, so it's going to be like a boundary layer. But you could imagine that this would be a contour of a small velocity going downstream into the page, and the fastest velocity would be this circle in the middle. If you looked at a section, it would be kind of zero velocity here, but perhaps not quite zero because there's a boundary layer, very thin boundary layer, which is there. And I suppose if you drew a vertical profile or a plan view profile, and you looked in plan view at the velocity versus location, then I suppose it would look like this, right? And symmetric on the other side. So the maximum velocity in the middle, zero velocity at the edges. This is plan view. Right there. So this is plan view. None of these are plan views. And likewise for this. And so around this boundary, there is very low velocity, perhaps zero velocity in all of these cases at the ultimate depth of the channel. Also at the channel wall as you go around it, as you can see here, this would be a velocity, maximum velocity in the middle, zero velocity is the edge, just here. And so as a result of that, you're applying a shear stress, not acting perpendicular to the boundary, but acting downstream. So this shear stress would be acting, coming out of the page at us, right, along this boundary. In other words, it would be acting in this direction here, right, all the way along here, providing drag against this motion. And so the bottom line is that we can do a simple force balance, not too much math today. So we can write momentum balance, which you might remember, sum of forces is equal to velocity times mass flow rate. Right? Remember this equation? So sum of forces acting downstream. So we take a block. This is our block, which is upstream, downstream. We cut it off. We look at the force which is applied on the upstream. We look at the force which is applied on the downstream. We look at the momentum going into it by the velocity going into that cut off volume upstream, the velocity coming out downstream. We could look at a shear stress. This is equal to shear stress tau acting on the bottom, if you can't see this. And we can do a mass balance. If we look at the sum of the forces, then, and we don't look at these ones on the base, then this would be, this is the mass flow rate. This is the velocity, so these two. We're resolving downstream. And so by definition, if the upstream and downstream velocities are the same, they have to be, because we're making them the same depth. So if V2 and V1 are the same, the right-hand side is equal to 0. If the right-hand side is equal to 0, then the forces are equal to 0. Good. So that's one first step we can make. Now we can go in and we can look at the force balance on this segment by putting in the other forces. The forces that we have acting would be F1 and F2 exactly balance each other. We can ignore these forces because, no, I don't think we can. We can now resolve in terms of the shear stress, which is acting against the downstream component of the weight of the water. So the weight of the water has a component which is downstream. It's on an incline. And so we can balance the forces acting along this direction. These two equal 0. We have a shear stress multiplied by a perimeter. I guess if I draw the perimeter of this would be this length here. Right? This is the perimeter times the length, which is this here. And so we can get rid of these two terms because we've shown that they equal 0 right here. And we're left just with that the shear stress is equal to, this is the shear force that's acting, shear stress times perimeter times length. This is an area, not divided by. And this is the component of the force acting downstream, the weight of the water and its component in the direction of the flow, which is W sine phi. And so these have to equal 0. So in other words, tau W is equal to W sine theta over PL, which is this. If we realize that sine theta is a very small angle, so this angle here is the same as this angle here, and it's also equal to what we've defined as S0. Right? In our previous slide, we had length, we have delta Z, and we had this magnitude was equal to S0, which is exactly what this is. So it's just this, for very small angles, this is equal to just this gradient. So both tan and sine equal just the magnitude of 1 foot divided by 1,400 feet. So it'd be whatever the relative magnitudes are. So we can convert this value here to just S0, and we're left with this. So what else do we need to do? So we have this defined here. We know that the weight is going to be equal to the cross-sectional area, looking down here, times its length, times its unit weight. So the cross-sectional area times the length, this is the volume of the fluid that's in that channel. This is its unit weight, and so we can just substitute for this value here. And so that would be this term here. Area times length this. We're not doing anything else. And so by definition, since the area of over the perimeter, this is equal to 1. Area of perimeter is just equal to our definition of hydraulic radius. So we have this expression here. So we know that the shear stress that's acting on the bottom of the bed is equal to hydraulic radius. the unit weight of the water, which we can get, and the slope, which we can get from the bed. If we want to define it in terms of the head loss in the system, you remember that we could write head loss is equal to loss coefficient v squared over 2g. Remember, for these were major losses, right, or minor losses. These are losses in fittings. This is equal to delta P over gamma. This is the head loss in a fitting. It's a coefficient which can be a maximum of 1 usually, and the velocity of flow in the fitting as it goes into it. So this is this. This is a variant on this. This is just describing the shear stress that's applied on the panel. This is the same as, I'm doing more than I really wanted to do here. So delta area times delta P. So if you imagine a pressure difference between upstream and downstream as delta P, the area times that pressure difference is the imbalanced force between upstream and downstream. That has to equal the shear stress times the perimeter times the length, right? So this would be the shear stress that's acting, this would be the perimeter around here, and this would be the length of the pipe. And so the pressure drop and the shear stress are related, and so that's where, from this expression, you can get this expression. That's where it comes from. Don't need to understand that, but we need to only do this. Take it on trust that this comes from our loss in a fitting. And if we can equate this to this, then we end up finally, if we solve for the value of the velocity in the flowing stream, just by rearranging this after making this substitution, this is what we end up with. Longer than 1 minute. And it says that, take square roots of both sides, velocity is equal to some kind of constant multiplied by hydraulic radius and the slope of the bed. So we can write it as this, the so-called Chezy formula, after a French fluid mechanician, I guess. And this is a constant, and this is the other term. It turns out that this constant isn't actually a constant. If you do some experiments in a flume to measure it, like you could do for measuring the friction factors in pipes, it turns out that it's not a constant, but it's a function of the hydraulic radius to the 1/6 times a roughness coefficient. This is termed the Manning coefficient. After, I guess, a British fluid mechanician. And this says something about, this is essentially the friction factor for a channel. So it turns out that this constant really isn't a constant that's independent of the terms in this equation, so you have to accommodate this r to the power 1/6. So this equation, instead of being equal to c times RH to the half, S0 to the half, this term here has to include the r to the 1/6, and so that's this term here. So instead of being hydraulic radius to the 3/3, so hydraulic radius to the 1/2, it's hydraulic radius to the 2/3. So this is where the extra 1/6 comes in. And so these are standard results that you can use. So to get the average velocity within the flowing system, you need the hydraulic radius of the pipe or the channel. Stop. It's misbehaving. Hydraulic radius is equal to the area times the perimeter, divided by the perimeter. So that's easy to get if you have fluid flowing in a river. You know what the gradient is, which is just this value on the bed, which is also the same as the depths of the flow as well. So it could also be that if you take the difference between the upstream and downstream, in this case, this is L, this is delta Z. For this case, this is equal to S over 0, this slope. We always define it as positive, and then you can calculate what the velocity is. If you want to get the volumetric flow rate, you multiply this by the cross-sectional area, and Bob's your uncle, as they say, allows you to get the behavior. So that's it. So for uniform flows, it's very simple. I guess we went through a bit more arduous derivation than I really wanted to, but the bottom line is you can get the velocity as a function of a coefficient, a Manning's coefficient, hydraulic radius, and the gradient of the bed. It turns out that these aren't non-dimensional numbers. So this is a length over time, but these units are not length over time. And so you have to, if you're using SI units, use meters a second, which we would use. And then, if that's the case, this coefficient kappa turns out to be 1. And if you use English units, you have to use feet and seconds, in which case this kappa turns out to be 1.49. So that's it. 3 minutes to go. Well, let's do it. So it's not very difficult. So these are the expressions you need to use if you're calculating what the velocities or the volumetric flow rates would be. If you look at realistic channels, these are values of this Manning's number. And so you remember that we kind of described them before as being on the Moody chart, that this was laminar and turbulent, and this was turbulent. This was Reynolds number. And so these would be values. So this would be weeds. This would be glass. And these would be numbers that go from, what's glass? 0.01 to weeds, 0.03. You never need to draw it like this, of course, but this just rationalizes it relative to the Moody chart, is that as it gets more, the channel sides get more rough, goes from glass to weeds, then the magnitudes of these Manning's coefficients change. Light brush is if it's going through trees, I guess. Heavy brush is if it's going through trees. So I guess this would be brush. Be much larger. And so if you have a channel, well, let's start there next time. So if your channel, you can calculate all these things. You know what the channel base is going at. You can calculate that elevation drop in a given length. So you have a value of S0. If you know how deep the flow is, you immediately have a hydraulic radius because you know the cross-sectional area of flow and its perimeter. And if you know what the channel is made of in terms of how rough it is, you have this. And it just becomes a straightforward calculation to do that. So let's rejoin that next time. Very easy. It's a recipe, very formulaic. Okay? Questions? Welcome back.